small for all this stuff to be big. And do we want to make this small? That depends on your application, but most of the time, if you want to, you generally want a shorter focal length just so you can get things to converge faster, right? A stronger lens has a shorter focal distance. What do we need for a stronger lens? Well then, we need a big N, an N that's much greater than 1. This is assumed to be for air, right? If it wasn't air, it'd be, it'd be the difference between your lens material and whatever the ambient stuff is. Let's say you're in water. You're trying to do stuff in water, right? Why don't your contact lenses work when you're underwater? Or why don't your eyes work, for that matter, when you're underwater? They're going through this lens of your eye, but the ambient is no longer 1, air. It's now like 1 point something higher, right? So this focal distance that you have set up for your lens doesn't work anymore, right? So this index of refraction is important, and the bigger the index of refraction, the better, right? The best glass, the highest quality glass, has the biggest N, index of refraction. That means that the light goes slower inside that glass compared to air or vacuum, for that matter.
That
So,
thing that
yeah.
that you were just erasing there. I'm sorry to interrupt, but I'm having a small issue with it. For step 3, you said if I is greater than 0, you have a real image, and if I is less than 0, you have a virtual image.
Did I say that?
Yeah. Was there something else?
I think, doesn't that agree with with what I just said? If I is greater than 0, then it's a real image, and if it's less than 0, it's a virtual image?
That's what you said, yeah.
That's what was up here also? No?
But then it also said if I is less than 0, or if I is greater than 0, it's upright, and if I is less than 0, it's inverted. And we have a couple of instances here where we've got eyes that are
Maybe I wrote that wrong then, because
Okay.
if I is a negative number, then it has to be upright.
Right.
And it has to be a virtual image. Let's write that down. If I is less than 0, right, then it's going to be upright, and it's going to be virtual, right?
Yes.
Right. Does that make sense with everything?
Yes.
Okay, good. Sorry if I wrote something.
Well, there was something that I wrote down that I'm just looking at the examples we did and
Right.
I disagree. So
Hopefully that agrees with everything.
Yes.
Good. I apologize if I wrote something different, but that's the truth right there. Okay, what about lenses? How do we do that? So, lenses. Same thing. We draw a primary axis and your lens. And then draw ray parallel to axis and goes through F. Right? So here's this lens, and let's say F is over here. Here's my object. Right? So this is P. And this is H of the object. So I go through here, parallel, and it goes through F. 3. Draw ray through center of lens. And it goes through unhindered. This is what happens through a lens when it goes to the center, right? Nothing changes. It keeps going through straight. So where's the image? Let's make this a little more horizontal. There's my image, right? Greater than F in this case. Now, sign conventions for lenses are a little bit different from mirrors. Very similar, but not the same. Let's just assume that we always say that P is greater than 0. We always put P on this side of the lens, right? That's just an assumption, and we don't have to stick to that, but we got to start somewhere. And then, if I is greater than 0, then the image is on the other side of the lens, right? It's over here. It's a positive number. And it's virtual if it's less than 0, and on same side as the object. If I is negative. Okay? And look at what happens over here. I is greater than 0. Let's do an example for this. Let's say that my F equals 10 centimeters and P equals, let's make this 20 centimeters. Then what is I? Well, we got 1 over P plus 1 over I equals 1 over F, right? So we got 1 over 20 centimeters plus 1 over I equals 1 over 10 centimeters. Notice the difference between the mirrors, right? What did I do here? In a mirror, if it was on the other side of the mirror, it'd be a negative F, right? But in this case, because it's a lens and the light actually goes through, we say that F is positive when it's on the other side. So let's put this in as well. 0. If F is greater than 0, it's converging on the other side of object. And vice versa. If it's less than 0, then the F is on this side, and it's a diverging lens. We'll do an example of that in a second. So then I, in this case, ends up being 1 over 10 centimeters minus 1 over 20 centimeters, right? Put that in the beam, let's see. 10 inverse minus 20 inverse of all that is 20. Great. So I got 20 centimeters for what my image is. It's a positive number. It's on the other side of the lens, right? Agrees with statement 2, right? Image is real, it's on the other side of the lens. Okay, great. And it's also upside down. So, once again, this is still true. Right? I is positive, P is positive. What's my magnification in this case? -1. -1 because it's upside down. It's a real image. What does that mean? That means if you stuck a screen over here, it would show up as a sharp image right here. Anywhere else off of this plane, it would show up as a blurry image. It wouldn't be focused. Okay? Let's do this worksheet business. here. An object has a height of 10 centimeters is viewed through a converging lens. Determine the location and height of the image for the following distances that the object is held away from the lens. Verify your calculations using these diagrams. Well, let's do the first one. So we got, once again, oops, let's make this a lens, not a mirror. And I get an f of 10, right? 10. And then I got my object that's 10 centimeters tall at 35. So I got 10, 20, 35. And it's this tall. Kind of make things big there. So then I draw these two rays, one that's parallel, and it goes through F. And then I draw one that goes to the center and keeps going. Right, so there's my image. That should be the top of the hand. Okay? So then, 1 over 35 centimeters equal plus 1 over I equals 1 over F, right? Which is 10 centimeters. And I should get a value for I. Like that. Okay, let's have you guys do a couple more down here. Take about 5 minutes, and we'll do get as far as we can on those in the next 5 minutes, and then we'll go through what we got. We have, what about if P is at 15 centimeters? So here's 10, and then I got another 10, I got P is 15 right here, right? And so I go here, through here, and then this has to go through here, right? And so your image should be right there. What do we have? We've got number 1 for I.
30 centimeters? Are you on the?
The 15 centimeter.
Yeah, 30
problem.
centimeters.
30?
Yeah.
Okay. Good. And And what about for 5? What if I put this thing really close? Halfway between the focal distance. Then what happens?
Maybe it's something.
It goes like this, and it goes like this, right?
Right.
Should be minus 10 centimeters. So here's my image. It's at the focal distance. It's twice as big because the distance is twice as big, right? And it's a negative number, meaning it's on the same side as the lens. Right, that's what that negative tells you. And then if I do the magnification, minus 10 centimeters over 5 centimeters, it's minus negative 10, right? 2. So it's twice as big, it's positive, it's upright. And so we should make sense of all these positive, negative numbers in terms of what it physically means on that lens diagram. I mean, you know, this lens equation, 1 over p plus 1 over I equals 1 over f, that's fairly straightforward math, but then you got to step back and always think about what it actually means physically. Okay, let's talk about diverging lenses. Let's talk about diverging lenses. So here's some diverging lenses. And, you know, I don't know, that didn't have a stock image for a lens that looks like a diverging lens, because that lens clearly looks like it's another converging lens, but diverging lenses probably look something like that, right? And so diverging lens, f is less than, sorry, not 10, 0. Less than 0. That means the focal distance is on the same side as the object. So if I have an image here, let's say f is here, and I have an object over here, what do? Well, I do the same thing as before. Do this. It's got to go outwards on the other side, but it's got to go through f, right? Like that. And then what? It's got to go here and through straight. And then we pretend like it's going to come back through here. So, where's my image? Somewhere over here, right? So here's the thing about a diverging lens. It's pretty much always going to give you an image that's virtual on this side, on the same side as the actual focal distance, is the same side as the object itself, right? Because what happens with a diverging lens, it's always going to make rays go outwards. And so for them to go outwards, they're always going to have to converge somewhere on the same side. Let's do this example over here. A diverging lens where f equals minus 10. The height is 10. Sorry, f equals 10, it should be minus 10. And determine the height and location of the image. If p equals 35 centimeters. So let's do this a little bit better scale. So this is f at 10. So we have 10, 20, 35, right? And it's 10 centimeters, so it's this tall. Alright. It's f is over here, right? There's this. There's that. There's that. then we get 1 over 35 centimeters plus 1 over I equals minus 1 over 10. Right? I equals minus 1 over 10 centimeters minus 1 over 35 centimeters. So we have to be careful with the signs here. Got 35 inverse, negative 35 inverse, minus 10 inverse, and then inverse all of that. It's minus 7.77. Right? Minus 7.77 centimeters. Right there. It's negative because it's inverted. It's negative because it's on the same side as the image. As the object, sorry. Right? So if you look at this number, this negative sign, it should tell you what that looks like based on those rules that we just went over. Right? Let's take a couple minutes and just do this last one right here. You guys do one of these. Let's do the 15 centimeter one. Let's get you guys practice. I gotta get out of here in about 5 minutes, so let's do this last example. Negative 6. Good. What is that going to look like? It's going to look something like, here's 15 centimeters away. Here's F over here. And go straight. Which is actually F over here. I don't know why I'm putting it there. Go over here.
Something about this isn't making sense.
Yeah, that's not right. That's not right. Let's go. It's been a while since I've done this one.
The picture seems like it's correct.
Yeah. Is that minus 6? Is that really minus 6?
Well, it is if you calculate that, but
Yeah.
should the focal distance be a negative number? Or should it be positive, making this turn out to be 30 centimeters?
Let's see, is that what's going to happen here? That? Is that true? Maybe true. Let's see. Let's look at our pictures over here and see. Goes over here. This goes over here. Oh, it goes back that way. That's what I was doing wrong. Correctly. So, it goes this way, and it comes back this way, so that's where the image is. Sorry, so I drew this incorrectly.
It reflects off of the center, right back toward the
Yeah.
object.
Yeah, that's what actually happens. It doesn't reflect down this way, it goes positive like that. So I drew that last one wrong. Same with the last one, so fix that in your notes on what I did the last time. So this is 6, right? Or minus 6. So that makes more sense, all right? Okay, so in this case, then we get a magnification that's the negative of negative 6 over 15, right? So it's smaller, and the image is upright, so it's a positive number that makes sense, and then it's also smaller than what we expected, and it's on this side of the lens, on the same side as the object, so that's why this is a negative as well. So, sorry about that, a little mistake on that. Hopefully that's corrected and cleared up, makes sense to you guys now. All right, that's it for today. I gotta go. Gotta get out of here. I need to be somewhere at 12 o'clock, so we'll adjourn, and we'll be back to Tony on Monday, or Tuesday, right?
Hey, man.